We can do considerably more to limit our search for candidate matches. The next step is to consider not only whether the prefixes of two strings have a symbol in common, but whether the first common symbol appears close enough to the fronts of both strings. The fact that no symbols before them are common to both strings will put a lower bound on the edit distance of the strings, and this lower bound, in turn, will place a lower bound on the Jacquard distance between the strings. When we use a two-dimensional index based on both the symbol at a position and the position number itself, we can cut down the total number of strings that become candidates for comparison with a given probe string, roughly by a factor of 2. Suppose we have strings S and T, and the first position of string S that matches a symbol in T is at position I. Moreover, this symbol, which we shall suppose is A, matches the symbol in position J of T. Then the first thing we can conclude is that S has I-1 symbols that do not appear in T, and T has J-1 symbols that do not appear in S. Thus, the edit distance between S and T is at least I plus J minus 2. While we have a lower bound on the edit distance, we can also see an upper bound on the length of the longest common subsequence in terms of the length L of string S. That is, the longest LCS we can have is when every symbol of S following the A also appears in T. These symbols may not be consecutive in T, but remember that there is a unique order to the symbols, and they appear in the same order in every string. So if S is of length L, then the longest possible LCS is of length L minus I plus 1. That is, all but the I-1 symbols of S that precede the symbol A. Now we can use the lower bound on edit distance and the upper bound on the length of the longest common subsequence to figure out for each position I what positions of J of the other string could be the first match. Remember, we observed earlier that the Jacquard distance of two strings can be expressed as E over E plus C, where E is the edit distance and C is the length of the LCS. So if J is the upper limit on Jacquard distance, we have E over E plus C is less than or equal to J. From the previous slide, we know that E is at least I plus J minus 2. And C is at most L minus I plus 1, where L is the length of the probe string S. These two inequalities let us get a lower bound on E over E plus C, which, using this, must be less than or equal to J. That is, if we hold C fixed and vary E, then E over E plus C is minimized when E is as small as possible, since C is non-negative. If we hold E fixed and vary C, then E over E plus C is minimized when C is as large as possible. If we let E be as low as possible, that is, I plus J minus 2, and we let C be as large as possible, L minus I plus 1, then we can treat these inequalities as equalities, substitute I plus J minus 2 for E in the inequality E over E plus C is equal to or less than J, that is this, and substitute C equals L minus I plus 1 in the same inequality, and we get this messy formula. Trust me, that's what you get. You can work it out yourself. But there's more messy math. Our goal is to isolate little j, so we can multiply both sides of the inequality by L plus J minus 1, rearrange the terms, and voila. You get an upper limit on little j, the position of the second string, such that I and j are the first matching positions of the first string. The right side of the inequality is messy in the extreme, but for a given position I of the first string, everything is known. We know the upper limit, capital J, on the Jacquard distance, and we know L, the length of the first string, so we can calculate the value of this formula. To take advantage of the limit on little j that we derived on the previous slide, we're going to create a more complicated index structure where buckets correspond to pairs consisting of a symbol A and a position I. To index a string S, we look at all the positions in its prefix. The definition of the prefix hasn't changed. It's still the floor of JL plus 1. Where J is the upper limit on the Jacquard distance and L is the length of the string S. We put string S into the bucket AI for all positions I that are part of S's prefix, where A is the symbol that S has in its ith position. Incidentally, we still recommend a B tree indexed by keys AI, ordered first by the symbol A and then by the position I. But there are many suitable forms of index structure, and the important thing is that given A and I, we can get to the bucket for A and I quickly. To exploit our upper limit on the value of little j, we're going to make use of the observation that given a probe string S, we only need to find a candidate string T that might be within Jacquard distance capital J of string T one time. We'll make sure we find T in the bucket for the first symbol it has in common with S, but we may not look for T in buckets for later symbols that S and T share, even if those occurrences are both within the prefixes of their strings. So we're going to visit the positions I of string S from the left, that is for I equals 1, 2, 3, and so on in that order. Suppose we find a symbol A in position I. Then we're going to look in certain buckets, AJ, to find candidate strings T to compare with string S. When we decide which buckets to look in, we can assume that none of the earlier positions of S, that is, the positions less than I, have matched anything in the candidate string T. If this assumption is wrong, then T is already a candidate, so we don't need to worry about missing T for this value of position I. That assumption lets us use the upper bound on J that we derived 2 slides previous. Here's the pseudocode for how we find candidate matches for a probe string S. First, we do a loop on the positions of I that are part of the prefix of S. This loop is just like the simpler form of lookup we described earlier. In particular, this limits I to be only the positions in the prefix of the string S. The first thing we do is determine the symbol A in the position I of string S. We need that to limit the buckets we search to only with the right symbol. Again, that's just like the earlier lookup. What's new is the inner loop on J, the position of the target string that might match the ith position of S. Notice that the loop limit is exactly the formula for the upper bound on J that we derived earlier. And for each value of J within its limit, we look in the bucket for symbol A and position J. Any string there becomes a candidate for being within Jacquard distance capital J of string S. Okay, so let's take an example of a lookup. We'll assume J, the upper limit on Jacquard distance, is 0.2. And here's our probe string. Its length is 10. And how long is its prefix? Well, JL is 0.2 times 10, or 2. Add 1 and take the floor, and you get 3. That is, the prefix is ADE. here's the upper bound on J, the positions in the buckets in which we have to look for a given I. Since we know everything but I, we simplify the expression to this. Remember, J has to be an integer, so for I equals 1, we get 3.8 minus 1 or 2.8 divided by 0.8. That's 3.5, so J is equal to or less than 3. Okay. For I equals 2, we get 1.8 divided by 0.8, or 2.25. Thus, J has to be 1 or 2. And for I equals 3, we get 0.8 divided by 0.8, so only J equals 1 will do. Of course, I can't be higher than 3 because the prefix of the probe string is only 3 positions long. But even if we were unaware of that, we'd get a negative upper bound on J for I equals 4 or greater. As a result, suppose again that this is the probe string. And consider I equals 1. The first symbol of the string is A, and if you remember the previous slide, we determined that for I equals 1, we need to look at buckets for J up to 3. Thus, we need to look in these 3 buckets for possible matches at Jacquard distance up to 0.2. For I equals 2, the upper limit on J is 2, so we look at these 2 buckets. And finally, for I equals 3, we look in the bucket E1, because E is the third symbol of S, and for I equals 3, the upper limit on J is 1. No other buckets have to be searched. We want to convince ourselves that when T is in none of these 6 buckets, then it can't be at distance 0.2 or less from string S. Then the edit distance between S and T is at least 3. To see why, consider what the first symbol T has in common with S can be. If it is an A, then that A is at least 4 positions back in T, because we would search for and find T if A were any of the first 3 positions, because we look at those buckets. If A is at least 4 positions back in T, then there are 3 symbols in T that precede A in the first symbol of S, and therefore there must be these 3 symbols of T must be deleted to convert T into S. Okay, if the first symbol that T and S share is D, then it must be at least 3 positions back in T, and therefore there are at least 3 symbols not shared by S and T, namely A, which is in S but not in T, and the 2 symbols in positions 1 and 2 of T. And similarly, if S and T share E but not A or D, then E is at least 2 symbols back in T, and we can identify A, D, and the first symbol of T as symbols not shared. And of course, if the first symbol S and T share is after E, then A, D, and E are not shared. And the LCS of S and T cannot be longer than 10, because that is the entire length of S. Therefore, the Jacquard distance between S and T, which is E over E plus C, is at least 3/13, which is about 0.23, and surely greater than the minimum distance between S and T that we will accept, which is 0.2. Thus, there is no reason why we should compare S with any T that is not in one of the 6 buckets we actually do search.